Okay, let's look at it. Here we go. We got another theorem. The fundamental theorem of algebra. The most basic theorem in the whole entire world that all of algebra is based on. Right here. Fundamental theorem. Says that a polynomial with degree n, so degree of whatever number, would have that same number of roots. Okay, so whatever the degree is however many roots it has. Now that doesn't mean that they're all real roots. Some could be imaginary, some could be real. They could all be imaginary. Complex roots with imaginary parts come in pairs. This is one important thing for today. Complex roots with imaginary parts come in conjugate pairs. If you have one complex root that's a plus bi, then you also have a root that's a minus bi. A minus bi. So if they tell you one of these, if they tell you, oh, a plus bi is a root, you automatically know another one because you know a minus bi is also one. That same thing is true if you have irrational real roots. They also come in pairs. If a plus b, if a plus the square root of b is a root, guess what's also a root? A minus the square root of b. Now, do remember, real roots correspond to actual x-intercepts on a graph. Guys, we done with our personal conversations? Thank you. All right, real roots correspond to x-intercepts on a graph. Complex roots do not. They don't have x-intercepts on a graph. You can actually take out imaginary roots using synthetic division the same way you remove real ones. Okay? It just involves some work with an I, which we know how to work with I. So this first one says, if negative 2i is a 0 of this polynomial right here, x to the 4th power minus 2x squared minus 24, find all the other roots. Well, first of all, if negative 2i is a 0, what's also a 0 then? Oh, yeah. I haven't written anything yet, bro. I literally... What's taking so long? Okay. If negative 2i is a 0, what's also a 0 then? 2i, right. Positive 2i is also a 0. Okay. So what we're going to do is since we know both of those are zeros, we can actually divide them out using synthetic division. Okay. Now when I get ready to set up my synthetic division for this first one here, is it missing a term? Yeah. It's missing 2 terms. Good job. What's the first one it's missing? 0x cubed, right? What's another one we're missing? 0x. If it's missing a term, we need to make sure that we put in a placeholder 0 for it when we do our synthetic division, just to keep everything aligned properly. So remember, for synthetic division, we're going to write just the coefficients. So we'll start at the beginning. The coefficient of x to the 4th is 1. And then we'll have a 0 for the x cubed. Negative 2 for the x squared. You don't need it on this one. 0 for the x. And then negative 24 is the constant. Okay. And again, what we're doing is we're taking out those 2 imaginary solutions that we already identified over here. So I'm going to start with, you want to do the negative one first or the positive one first? It doesn't really matter. What'd you say? You said negative? I heard it first. All right, we're going negative. I heard it first. Sorry, Quinn. Okay, our process for our synthetic division is going to be the same. We're going to start by bringing down this 1 here. Okay, and then we're going to multiply. Negative 2i times 1 is negative 2i. Okay, and then we're going to add these 2. 0 plus negative 2i is negative 2i. Right? 0 plus negative. Okay. And then we're going to multiply. Negative 2i times negative 2i would be positive or negative?
It would be positive.
It would be positive 4i squared. I'm going to write it down over here so we can show the little calculation. What is I squared? It's negative 1. So that's actually 4 times negative 1, which is negative 4. So negative 2i times negative 2i is actually just negative 4. Again, we did that little calculation over here. It was 4i squared, which I squared is negative 1. We multiplied and got negative 4. And then what do we do with negative 2 and negative 4? Add them, which is negative 6. And then we're going to multiply negative 2i times negative 6 is 12i. And then we're going to add those and get 12i. And then we have another where we have to multiply 2 with i's. Negative 2i times 12i would be negative 24i squared, which should be negative 24 times negative 1, which is a positive 24. So this times this was positive 24, and we got 0, which we should have gotten a 0. They literally told us it was a 0, which means it should not have a remainder. So that's kind of a hint, like if you ever did get a remainder on that, on one they tell you does work, it means you did something wrong. So we took out, it was a fourth degree, and we took out one root. So technically, what does this represent now? It's not a quadratic, it was a fourth degree. And we took out one. Yeah, it's to the third power, which would be called a cubic. So these now represent the coefficients of a cubic. We don't need to write it, though, because we still have one more root that we need to take out. What was the second one that we found? Positive 2i, right. And we're going to build the synthetic division right onto here. You don't have to do a whole new one. Just build it on. Okay, and this time I want to take out positive 2i. Yep. Okay, everybody setting it up? Okay, so kind of ignore the first one now. We're just focusing on this one. I'm going to start by taking that 1 and bringing it down. And then we'll do 2i times 1, which is 2i. And then we're going to add these two to get 0. Yeah, you have 2i plus 2i is 0. Then we're going to multiply. 2i times 0 is 0. We're going to add those two to get negative 6. We're going to multiply. 2i times negative 6 is negative 12i. And when we add those, what do we get? 0, which again we should get 0 because they literally told us, hey, it's a root. Okay, so we were at a fourth degree function. We took out a root and got a cubic function. We took out another root, so what should these now represent? Quadratic, yeah. These should now be a quadratic, a squared function. Okay. Now if we wrote this quadratic, we would have 1x squared and 0 x's. So do we need to write them? No. But we would have negative 6. 1x squared and minus 6. On this question, we are asked to find the roots, which means we need to actually find the solutions. Okay. So last thing we need to do is we just need to take this and solve this. Okay, so to solve it, I need to set it equal to 0. It's actually really easy to solve this one. Anyone know what we would do next? Don't have to do quadratic formula. Do what? Add 6. Yep. Isolate the square. This is one of the easiest ones to solve, but one of the ones that most people forget how easy it is. So that gives me x squared equals 6. And then we'll do what? Square root. And we'll get x equals what two numbers? Plus or minus square root of 6. So if I were to make a list of all of those roots, all of those zeros, we've got positive and negative 2i. And we also had positive and negative square root of 6. If this was a fourth degree polynomial from the start, how many solutions should it have? It should have 4. Does it have 4? It sure does. They're gross 4, but it is 4. Alright. Next up, we're going to learn about Descartes' rule of signs. Descartes was a mathematician. Descartes. Guess what his last name was? Descartes. And this is his rule of signs that he discovered. Again, they didn't have TV and phones back in the day. They had to just play around with numbers a lot. Descartes' rule of signs tells us how many positive and negative real zeros a polynomial could have. Okay? It's all the possibilities of what they could have. It doesn't necessarily tell you what they are, it just tells you how many it might have. The number of positive real roots, I'm going to read this and you're going to go, huh, and then I'll explain it. Okay? It's either equal to the number of sign changes in a polynomial, or it's less than that by an even number. And I know what you're thinking. What, Ms. Reddy? So what it means is you're going to count the number of times that the signs change in your polynomial. So when it goes from a positive to a negative, or when it goes from a negative to a positive, that counts as a sign change. So this one right here would go from a negative to a positive, that's 1. A positive to a positive, that's not 1. But then a positive to a negative, that's another 1. So what that means is that whatever this polynomial is, it might have 2 real roots, or it might have something smaller than this by an even number. And what's the only even number smaller than 2? 0, yeah. So it might have 2 positive roots, or it might have 0 positive roots. That's what they discovered back in the day. Fascinating, right? And it works the same thing for negative real roots. Okay, negative real roots. The first thing you would have to do for negative roots is you have to actually evaluate your function for p of negative x, aka plug in negative x to your function, and then count the sign changes. And then it's the same thing. You just say, how many times does it change signs? And then it'll be smaller than that. Like say you get 3. If you got 3, then it might have 3 negative real roots, or it might have smaller than 3 by an even number, which means if you count down by 2's. So if you count down by 2's, that means 3 or 1. Let's try one. I know you're thinking, what in the heck, Miss Brody? Here we go. All right. We're just trying to figure out how many positive or negative real roots it can have. Not even what are they, just how many could it have. And we're going to do that by counting sign changes. Okay. Starting with sign changes as it is now, because sign changes as it is now helps us find our positive. All right, let's go through and count sign changes. We went from a positive to a positive. Is that a sign change? No. And then we went from a positive to a negative. Is that a sign change? Yes. I'm going to mark that down. That's 1. And then a negative to a negative. Is that a sign change? No. And then a negative to a positive. Is that a sign change? Yes. So that's 2. So the number of positive real roots, there might be 2, or it might be smaller than that, counting down by 2's. What would be smaller than this counting down by 2's? 0. All right, 2 or 0. Those are the possibilities. Which means that it can't have 1. If you find 1, there's got to be another one, because the only possibility is having 2 or 0. For negative real roots, negative real roots. First thing we need to do for negative real roots is we need to evaluate this function for negative x, meaning plug in negative x everywhere we see an x. Here, 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 and here. Plugging in negative x. So we'll have 2 times negative x to the 4th power plus 5 times negative x to the 3rd power minus 18 times negative x squared minus 19 times negative x plus 42. And we're going to simplify this. Starting with negative x to the 4th power, what would that simplify to? Negative x times negative x times negative x times negative x would be positive x to the 4th power. And then we have positive x to the 4th power times 2, which is 2x to the 4th power. Okay. Next term, we've got negative x to the 3rd power. That would be negative x times negative x times negative x, which is negative x to the 3rd power, times a positive 5 would be negative 5x to the 3rd power. My nose itches. All right, next one, negative x squared. That would be positive x squared. But positive x squared times negative 18, negative 18x squared. Okay, next one, negative 19 times negative x, 19x. And then plus 42 at the end. Now we can count the sign changes on this one. Starting at the beginning. Positive to a negative, is that one? Yes. Negative to a negative, is that one? No. Negative to a positive, is that one? Yes. And then positive to a positive, is that one? No. So this one is actually the same. It has either 2 or 0. So it always is 2 or smaller than that, counting down by 2's. We might come back to this one. There's more we could do on it. But we'll come back to it. All right, same thing on these. We want to just count the positive real roots, negative real roots, and complex ones. We're not actually finding them. We're just counting how many it could have. Notice when it's missing a term, that actually doesn't affect it. You don't have to put in a 0 for missing terms or anything like that. You can do it just as it is now. So I'm going to start with positive, which means we're going to count the number of sign changes as it is right now. How many sign changes we got? Just one. And I'm not going to be able to count down by 2's on this one because that leads me to the negatives. Can't do that. So it's just one. It has to have one positive real root. And then for negative real roots, what do I have to do first for negative real roots? Plug in negative x. So we'll have negative x to the third power plus 2 times negative x minus 11. So negative x to the third power, that would be negative x to the third power. 2 times negative x would be minus 2x. Okay. And then bring down our minus 11. How many sign changes we have? 0. Yeah. 0 sign changes means you're going to have 0 negative real roots. If you don't have any sign changes, there's not going to be any. So if you had to make a list of p over q's and start guessing numbers, should you guess any negative numbers? It doesn't have any negative real roots, right? Notice on this one we have to do positive, negative, and complex, which would be your imaginary. So I'm going to make myself a little table for this. Positive, negative, and imaginary. I know that I have one positive real root and I have 0 negative real roots. But according to the fundamental theorem of algebra, this exponent tells me how many I should have total. You should have 3 total. So if I have 3 total, actually I'm going to even put a total column over here. Let's do it. Total. How many of those should be imaginary then? 2. Very good. Because we have to have 3 total, so 1 positive, 0 negative, 1 imaginary, 3 total. There it is. Again, we're not actually having to find them on these questions. We're just making a table. Ready for the next one? Let's do it. Again, it doesn't matter if it's missing a term on these. You're just counting the sign changes as it is now. I'm going to start with my positive real roots. AKA sign changes currently. No changes on it. Positive to negative, that's 1. Negative to positive, that's another 1. Positive to negative, that's another 1. And negative to positive, that's another 1. So it might be 4, or it might be smaller than that, counting down by 2's. So it could be 4, or 2, or even 0. Total has to be the highest degree. Well, these are just possibilities. Because, oh, actually, let's see that though. Let's see. Look at Jay being all smart. Stop being smart, Jay. All right. Negative real roots. Okay, what do we need to do for negative real roots? Plug in negative x first. So that's 2 times negative x to the 4th minus 8 times negative x cubed plus 6 times negative x squared. I've run out of room. 3 times negative x plus 1. What's negative x to the 4th power? Negative x. It would be positive x to the 4th power. Times 2 would be 2x to the 4th power. Good. Next up, what's negative x to the 3rd power? Negative x to the 3rd power. And then times this negative 8 would become positive 8x to the third power. Next up, negative x squared. Negative x times negative x is positive x squared. Times 6 is positive 6x squared. And then negative 3 times negative x, 3x. Plus 1. How many sign changes do we have? 0 sign changes. Way to go. Which means we won't have any we won't have any negative real roots. It's just 4 or 2 or 0. Let's make ourselves a little table. Positive. That is not, I wrote pot. It's not a bad word, guys. Positive, negative, imaginary, and total. All right, I've got 3 possibilities for positives. It could be 4, it could be 2, it could be 0. What's always my possibility for negative, though? 0 all the way down. No matter what the positives are, I know I have 0 negatives. How many should I have total according to my fundamental theorem of algebra? 4 total. Okay. So if we happen to get 4 positives, how many imaginaries would there be? 0. If I happen to get 2 positives, how many imaginaries would there be? 2. And then if there's 0 positives, how many would have to be imaginary? 4 to get a total of 4, right? I also feel the need to make this one a table since I made the last one a table, so you'll have to excuse me while I do that. Can't just have one table. All right. Before we do the last one, I'm going to go back and have us look at the one question that we did right before this, where we just wrote the positives and negatives. Go back to the previous side. Okay. On this one, we got 2 or 0, 2 or 0. I want us to think about what would the table look like on this one for positives, negatives, imaginary, and total. Now, if I have 2 positive, question first, how many should I have total? 4 total. If I have 2 positives, I actually have 2 different possibilities that could be paired for my negatives. If there's 2 positives, what are my options for negatives in this situation? 2 or 0. So I need to write 2 positive, it could be 2 negative, or 2 positive, it could be 0 negative. So notice this has to pair with both of these. Same thing if there's 0 positives. 0 positives could still have 2 different possibilities for negatives. You could have 0 positives and 2 negatives, or you could have 0 positives and 0 negatives. We know there's got to be 4 total. So if we happen to get 2 positive and 2 negative, how many would be imaginary then? 0. If we got 2 positives and 0 negatives, we'd have 2 imaginaries. If 0 and 2, then you'd have 2. Or the last one, if you got 0 positive and 0 negative, you'd have 4 imaginary. If you had 4 imaginaries, they'd have to tell you one to start with in order to solve it. Like, there's no way to just, like, guess it. Almost done. Alright. Find all the roots, real and complex, of the polynomial. So again, we know some starting things we can do on this. First thing I'm going to start by doing is just figuring out how many would be positive or negative. Okay, so for positive, I'm going to count those sign changes as it is written now. How many sign changes do we have? 4. So we might have 4 positive real roots, or we might have 2 or 0. And for negative, I'm going to start by plugging in negative x and then simplifying that. Negative x in parentheses to the 5th power would just simplify to negative x to the 5th power. The next one, negative x to the 4th, would turn positive, but then times this negative 2 would be negative 2x to the 4th. Okay. Negative x squared would be positive, times positive 8 would still be positive. And then negative 13x times negative x would be a positive 13x plus 6. How many sign changes do we have? 1. So there has to be one negative number that's a root. One negative number. That's it. No more than that. No less than that. No more than that. Next up, if we need to fully factor this, find all the roots, I need to make my list of P over Q's. Just like we did on the first notes. Possible roots. P is going to stand for factors of what number? 6. And Q stands for factors of the leading coefficient, which is just a 1. And remember, it can be both positive and negative of all these numbers. What are my factors of 6? 2, 3, 1, and 6. And then factors of 1, just 1. Okay. And remember, we also want to make a list of numbers we are testing, numbers we've tried, so we know what works, what doesn't work, so that we don't have to guess numbers that we've already done. Are we missing any terms that we might need to write in a 0 for when we do our synthetic division? Cube. So I'm going to make sure I do 0x cubed when I set up my synthetic division. Just grabbing those coefficients, we'll have 1, negative 2, 0 for the x cubed, 8, negative 13, and 6. And then we're switching to pencil, guys. This process will work a lot faster if y'all help me out and just start guessing some numbers that are in our list. Okay? If we want to sit here and guess all day long, we can guess all day long. But if y'all want to like work on your own and find some numbers, work on your own and find some numbers, work on your own and find some numbers, and then if we could all just tell each other what numbers we found that worked, then that's going to be helpful. Okay. How about, let's do Max, Francis, y'all, have y'all tried one yet? No. Okay, y'all check 2. Reese, Max, y'all's group check 3. Y'all check 1. Y'all check 6. Okay. Y'all check negative 2. Y'all check negative 3. Y'all check negative 1. I'll check negative 6. Okay. Everybody's checking a number. We're going to give each other our guesses and our no's. Use pencil, just in case it doesn't work. Got negative 1. Wait 1 second. Wait 1 second. I still gotta check mine. No, it ain't gonna work. No, not gonna work. What about it?
Why do we have to divide?
Oh, because it actually said find all the roots. Actually find them, not just tell me what are the combinations. Alright. Alright, let's go back through it. Max, Francis, y'all's group check 2? Did 2 work? 2 did not work. Okay. Lambert said what doesn't work? 3 doesn't work. What'd you get? 1, and 1 worked? Okay, 1 worked. What'd y'all check? 6, did 6 work? No. Okay, what'd y'all get? Negative 2, did it work? Okay, and then what else? Negative 3 did not work. Negative 1 did not work. Okay. So we got 1 worked. Let's go ahead and take 1 out since we were told 1 works. I'm taking out the 1. 1 times 1 is 1. We're going to add and get negative 1. That would be -1. We're going to add and get -1 again. -1, add, get 7. 1 times 7 is 7. Add, get -6. -6, 0. Excellent. Okay, if this was a 5th degree polynomial from the start, and we took out one root, what is it now? It's a 4th degree polynomial. Anyone know the name of a 4th degree polynomial? Quartic. It's like a quarter. Quartic. Okay. And what are we trying to get this down to? Quadratic. We still have some room to go. Okay, I will tell you, in this list we found one that works. We said everything else doesn't work. One of y'all lied. There is another one from this list that works. So one of y'all got it wrong. We double checking? Double checking? Everyone double checking. Double checking, because one of y'all lied. There is another number in this list that works. Aside from y'all's group, this did work. Good job. Double check your numbers. One, we already know one works. Everyone's double checking. You double check 3 doesn't work? Thanks, Max. Oh, -2 does work. Imagine that. Good job. Way to go, guys. Proud of y'all. -2 does work. We're going to erase that x. We're going to put a check, and let's take it out. We're going to build it right onto the ones we already have. Just continue it on, taking out that -2 that we found out that works. Let's see, -2, add, that's -3. Multiply, add. I know sometimes you're doing so much little baby calculations that your brain just flips for a second. Alright, it was a quartic. We took out one more root. What is it now? Cubic. Okay. Now let's look back at our Descartes rule of signs over here real quick. Okay. We know, according to this Descartes rule of signs, that we should have one negative number that does work. Did we get one? Yeah, -2 worked. So we had one negative root. We found it. This right here. It works. Go us. But how many positives should we have? Yeah, we can't. If we found one, then we know it's not 0, which means it has to either be 2 or 4 positive real roots. So I know there's at least one more positive number that works. There's at least one more positive that works. Now, does that mean someone who checked positives did it wrong? No, it doesn't. What that actually means is if a number works once, it could work again. Could work again. A double root. Okay? So I'm going to check this one again and see if it works again. Okay? Because I know I can't just have one positive number. I have to have at least 2 or 4 positives. Okay, so I'm checking one again. Just building it on to what we have already. Did it work again? Hallelujah. Which means this was a cubic. We took out one more root. What is it now? Quadratic. Yep. Switching back to my pen now. Okay. We are asked to find the roots, not just the factors. Find the roots, which means we need to find the actual solutions. So this would be 1x squared minus 2x plus 3. And we need to solve it because we're asked to find the roots. So we need to set it equal to 0 so that we can solve. Doesn't this look very factorable? It's not. It's not. Doesn't it look like it is, though? Those tiny little baby numbers. Two numbers that multiply to positive 3 and add to negative 2. There's not any. Bummer. How do we solve it then? Quadratic formula. Quadratic freaking formula. X equals, what does it start with? Negative of my b plus or minus. Yeah, b squared minus 4 times a times c all over 2a. So that's 2 plus or minus, that would be 4 minus 12, negative 8 over 2. Negative 8 square root, how can we simplify that? We're going to write that as square root of negative 1 times, there's a perfect square factor in 8 though, 4 and 2. We'll take out the square root of negative 1 as what number? Imaginary. Which other one are we going to take out? Take out the square root of 4 as a 2. And what's going to stay in there? The 2. So all of this is what's going to go here. So it'll be 2 plus or minus 2I root 2 over 2. Does this simplify more? Yeah, it does. So you can split it up. You would have, the first fraction would be 2 over 2 plus or minus 2I root 2 over 2. Most common mistake right here is people just scratch out 2 over 2 and they drop it. And if you drop it, you're saying it's a 0, and it's not a 0. What's 2 divided by 2? It's a 1. Plus or minus. What simplifies on that back one? Yeah, the 2's. So that would turn into I root 2, which definitely means it was not factorable. All right, let's write all the roots all together. The double root you do not have to write twice. What I usually do is I'll write it once and then I'll just remind myself that it was a double root. So I know I had negative 2. I had 1, which was a double. I'm just going to write it there. Double. And then we had this gross thing over here, this complex 1 plus or minus I root 2. We did it. Hardest question of the day, hardest question that we'll probably have in a long time. We survived.